Good afternoon. Let's start chapter 23 about blood vessels. Your blood vessels are composed of artery, vein, and capillaries. For now, we're going to focus on the structure of the artery and vein, and then we're going to add the capillary to this discussion. Both artery and veins are composed of three layers. Each layer is called tunica. So we have tunica intima, tunica media, or middle layer, and tunica externa, or outer layer. Before we go through all these three layers, let's take a look at the picture here and compare the artery to the vein. The difference, as you can see in this picture, is the artery has a smaller lumen compared to the vein. Vein has a very large lumen. The second difference that you see here, the tunica media, is much thicker than tunica media here. You will see tunica media is all a smooth muscle. The third difference that you see here is artery doesn't have any valves, but you may find valves in many veins. You may also notice that the tunica externa in the case of artery is pretty thin, but in case of vein is pretty thick. If you pay more attention, you may see that in the wall of the artery we have some elastic fibers, but you don't see it in the wall of the vein. So knowing all these differences, let's start with tunica intima. Tunica intima, which is the innermost layer of the vessel, is composed of endothelium. Endothelium is a simple squamous epithelial tissue that lines the vessel. You heard this word before. We talked about endothelium in the case of heart. We said endothelium lines the heart. So endothelium is a simple squamous epithelial tissue that lines the blood vessels, and also your heart is lined by endothelium. Outside endothelium, we have subendothelial layer. As you can see, you can find endothelium in the vein, and also you can find subendothelial layer here. However, outside of subendothelial layer, you have internal elastic lamina. Internal elastic lamina is found only in the artery, but not in the vein. Therefore, we say tunica intima is composed of endothelium, subendothelial layer, and internal elastic lamina, which is found only in the artery. Tunica media, on the other hand, or the second layer, is composed of two structures. The main one is the muscle, is a smooth muscle. As you can see, a smooth muscle in the case of artery is pretty thick, in the case of vein is pretty thin. However, in the case of artery, we have another elastic lamina here, and that is called external elastic lamina, which is not found in the vein. And finally, we have tunica externa. Tunica externa is the last layer and is composed of connective tissue. This tunica externa, in the case of artery, is not as thick as the vein. As you can see, under tunica externa, you have a word is called vasa vasorum. What does that mean? Well, remember that blood vessels, they are carrying blood, and blood has oxygen. But do you think the wall of these blood vessels, let's say this is smooth muscle, the cells of this layer, do you think those cells, they need oxygen and nutrition? So where are they going to get their oxygen and nutrition? If you think that they're going to get their oxygen and nutrition from the blood, which is inside the blood vessel, you're wrong. Remember, I told you before, if you are a banker, you cannot use the money in the bank. You have to have your paycheck. So who is going to supply oxygen or nutrition to the wall of this blood vessel? The answer is a very tiny blood vessels. It's called vasa vasorum, or the vessels for the vessels. As you can see in this picture, it shows vasa vasorum in the wall of tunica externa. So tunica externa contains vasa vasorum. I'm sure many of you realize that when you want to take a pulse, you use artery, not vein. You don't feel pulse through the vein, but you feel pulse through artery. Why is that? Because when the blood comes to artery, it's going to push the wall of the artery. And because artery has elastic lamina, it's going to bounce back. The wall of the blood vessel is going to bulge out, and then it's going to bounce back. That's how you're going to feel the pulse. But you don't feel the pulse over vein, because vein doesn't have any elastic lamina. So it's not going to bulge out and then bounce back. And finally, I have to mention that in majority of the veins, but not all, you may find some valves. These valves are extensions of endothelium of the tunica intima. Now, between the artery and vein, we have capillary. The capillary is a place for exchanging oxygen and nutrition and waste. That means the wall of the capillary must be very thin to allow diffusion. Therefore, it should be no surprise to you that the wall of the capillary does not have these three layers that we mentioned. The wall of capillary is only composed of endothelium, and outside the endothelium you have a basement membrane. It's pretty thin because we need to do exchange. As a result, capillary has no tunica media or tunica externa. It simply contains endothelium and the basement membrane. This is a slide of a histology for artery and vein. Your lab instructor is going to go through this one with you. I just want to show you that the lumen of the vein is much larger than the lumen of the artery. The thickness of the artery is prominent, and it shows here the wall of the vein is very thin. So you're going to learn more about this one in your lab hours. This slide is going to compare artery to vein. I think I mentioned pretty much everything about this one, except I didn't mention that blood pressure inside the artery is higher and the vein is much lower. And that makes a lot of sense because remember, by definition, artery is going to take the blood away from the heart. So therefore, artery is closer to the heart. When the heart pumps blood inside the artery, the pressure inside the artery is going to go up. After artery turn into capillary and then it's going to turn into vein, of course we are staying away from the heart, and as a result the blood pressure inside the vein is much lower. The average blood pressure inside the artery is around 90 millimeters of mercury, but as you can see in the vein is about 2 millimeters of mercury. The rest of them is self-explanatory. You can read it yourself and summarize the information we just mentioned. Now let's focus on the artery. We have three types of arteries. We have elastic arteries, we have muscular arteries, and then we have arterioles. So what are these? Let's take a look at this picture. Here is your heart, and this is the biggest artery that we know is called aorta. Now think about it. Every time heart beats or heart contracts, it's going to push around 80 to 100 ml of the blood inside the aorta. Aorta must have a very good elasticity, otherwise aorta is going to rupture. If the aorta is stiff, cannot accommodate for all this blood. So when blood comes inside the aorta, you expect aorta to accommodate that blood. In other words, it has to show elasticity. So what type of artery do you think this one is? This must be an elastic artery. An elastic artery is an artery that has a lot of elasticity. Usually this artery is found closer to the heart. However, when branches come off from the aorta to go to the organs, those arteries that branch off from the aorta and goes for an organ, those are muscular artery. Why is that? Because they have a lot of muscles. They still have elasticity, but not as much. Their wall is very thick and is composed of lots of smooth muscle. Why is that? Well, the simple reason for that is we have to be able to control the amount of blood that goes to each organ. To control blood flow, we have to make sure your blood vessels has enough muscle to close off or opens up and give more blood to the organ. The wall of this muscular artery is innervated by sympathetic nervous system. Mainly the function of the sympathetic would be constriction of blood vessels. However, you may learn some exceptions later in physiology. And finally, the smallest branch of artery before we get to the capillary is called arteriole. Arteriole still has these three layers, but as you can see, arteriole doesn't have elastic laminas. Now let's talk about capillary. As you can see in this picture, this is the arteriole, this is the venous side, and this is your capillary. The extension of the arteriole that opens to the capillary is called metarteriole. At the beginning of each of this capillary, you have an sphincter. This sphincter can close off the capillary. If the sphincter closes off, blood is going to come from the arteriole to mid-arteriole, and without going through the capillary, is going to go directly to the venous side, just like this picture. As you can see in this picture, your sphincters are closed off, and blood is going to go through mid-arteriole and is going to get to your venous side. This bypass of capillary is called shunt. Shunt is when you bypass the capillary and gets inside the vein directly. Now, since we said this one, let's add another term here. The smallest vein is called veniole, just like the smallest artery is arteriole. So this one is the smallest vein, it's called veniole. The counterpart of mid-arteriole in the venous side is called trophary channel. So trophary channel is a counterpart of mid-arteriole in the venous side. We have three different types of capillaries. One is called continuous capillary, another one is called fenestrated capillary, and the last one is called sinusoid capillary. What's the difference between these three types of capillary? Continuous capillary is the most common type of capillary. Between the cells of the wall of this capillary, between these endothelial cells, you have tight junction. So there is no gap between the cells. Cells are attached to each other tightly. If you ask me how this oxygen and nutrition is going to get through this capillary to the cells outside, the answer would be through simple diffusion or through pinocytosis. The second type of capillary is called fenestrated capillary. It's called fenestrated because, as you can see, there's a bunch of holes in the wall of this capillary. The exchange of the oxygen and nutrition with the outside would be easier because we have a bunch of holes. However, the exchange is limited to the molecule that can go through these holes. If the molecule like protein is too big, they cannot pass through these holes. And finally, we have sinusoid type of capillary, that there is a huge gap in the wall of this capillary. Therefore, much bigger molecule or cells that can pass through these holes and get in and out of the capillary. As you can see in these three pictures, in the case of sinusoid, the basement membrane is discontinuous to allow a big gap in the wall of capillary. But as you can see in the case of fenestrated or continuous, the basement membrane is intact. Where do you find this type of capillaries? Continuous capillary, which is the most common type of capillary, is found in the muscle, connective tissue, or exocrine gland. On the other hand, fenestrated capillaries are found in the endocrine organs, small intestine, or inside the kidney. We have a structure called glomeruli. We're going to talk about this one later. And finally, sinusoid is found in the liver, spleen, and bone marrow. And that is going to bring us to vein. Of course, after capillary, blood is going to reach to the vein. As you saw here, the lumen of the vein is pretty large. Therefore, veins are used as reservoir for blood. 60% of your blood at any given time is found inside veins. The smallest vein is called veniole, and the smallest veniole, of course, is found right after capillary. Remember the word diapedesis? It simply means when the white blood cells leave the blood vessels and get to the interstitium. Diapedesis happens in the post-capillary venules. If you look at this picture, you can see, of course, a bunch of arteries. Blood will be pumped by the heart inside the artery. So let's say this blood is going to come inside the aorta and it's going to finally reach to your toes. From here, blood from the artery is going to reach to the capillary, and then it's going to come back through the vein back to your heart. So now, obvious question is, how come this blood can move up against gravity and reach to your heart? If you're thinking that the heart is going to pump and that's the force of this contraction that push the blood down first through the aorta and inside the arteries, and then the remaining of the force is going to push this blood up against the gravity to reach to the heart, you're wrong. Heart cannot push blood that allows this blood to go against gravity and come back to the heart. So now the question is, how blood can go against gravity and reach to the heart again? Well, the complete answer to this question would be for the physiology, but briefly I'm going to tell you that in the lower extremity, when the vein is going through your legs and pass in the middle of the muscles. When your muscle contracts, it's going to squeeze this vein. Just like when you squeeze a toothpaste. If you open the cap of the toothpaste and you squeeze a toothpaste, of course the content is going to come out. If you cut the bottom part of the toothpaste and then you squeeze it, of course the content is going to get out from the top and from the bottom. With the same token, if you squeeze this vein, where this blood is going to go? Well, you're thinking blood is going to go up and should also go down. But you don't want this blood go down, you want this blood go up toward heart. So what's the solution? The solution is having valve here. The valve in the vein is a one-way valve and prevents backflow. And as a result, just like a toothpaste that the bottom part is sealed, there's only one way for this blood to go, and it's up. Therefore, muscle pump is one of the most important reasons for blood to go up back to the heart. Have you ever seen those guards in the front of a palace? They don't move, they don't blink, they stay there still. But you know that they're going to rotate very fast, very quickly. Because if you stand up without moving for a long period of time, then you're going to faint. Why? Because if you stand up without moving, you're losing your muscle contraction. You're losing your muscle pump. As a result, blood cannot go against gravity. So therefore, it's important for all of us to move and walk and use our leg muscles, because that is going to push the blood up to the heart. The second reason for this blood to go back to the heart is because of the function of the chest and lung. When you breathe in, your chest is going to expand. And when your chest expands, the pressure inside the chest will decrease. Remember, when the volume increases, the pressure is going to decrease. So when the chest expands, the volume increases, but the pressure decreases. When the pressure inside the chest decreases, that low pressure acts like a vacuum and pulls blood back to the heart. So therefore, we call this one a respiratory pump. You must understand, every time you breathe in, you increase the size of your chest. As a result, the pressure inside the chest drops, and that is going to create a small vacuum to pull blood back to the heart. And the last part of this discussion would be about blood pressure. To take blood pressure, we're going to use something that's called sphygmomanometer. And when you take your blood pressure, you have two numbers in a form of fraction. The top number is called systolic blood pressure. The lower number is called diastolic blood pressure. A systolic blood pressure is when the heart contracts and pushes the blood inside the blood vessels. Diastolic blood pressure is when heart is not contracting, heart is in relaxation, but still blood is going to put pressure against the wall of the blood vessels. As a result, it's going to create another pressure. It's called diastolic. No wonder systolic is always bigger than diastolic. Now, if you look at this diagram, you can see x-axis shows different type of the vessels. Let's assume here is your heart, and the heart is going to pump inside the aorta. Blood is going to go to the artery, and then arterial, capillary, venule, and finally it's going to get to vena cava and back to the heart. So that shows the sequence of the vessels. The y-axis shows the blood pressure. Now let's focus on the systolic blood pressure, this one. At the beginning of the aorta is around 120 or 125 in this case. As you stay away from the heart, clearly you can understand that blood pressure slowly is going to drop because you're staying away from the source of this contraction. But it's not going to drop significantly, slightly drop. Let's say in the case of artery, the blood pressure that starts from 125, let's say 122, now it's going to be around 110. So it dropped, but not significantly. But look at the arterial. Arterial, which is from here to here, as you can see, blood pressure at the beginning of arterial is around, let's say 95. But by the end of arterial, it's going to drop probably around 37. It's a huge drop from 95 to 37. That's the biggest drop that you see here. Look at the curve, how sharply it's going to drop. Why is that? Well, because Right after artery, we have capillary. And I'm sure you all remember that capillary has a very thin wall. If the blood with a high pressure enters the capillary, it's going to rupture the capillary. So arterial is going to act like a speed bump to make sure when the blood gets to capillary has low pressure. The pressure inside the capillary, as you can see, is somewhere between 37 to 17. So it's a very low pressure, with some exceptions, but majority of the time would be somewhere between 20 to 40, if you will, or 17 to 37. This is a low pressure. And again, the reason the pressure inside the capillary is that low is because of the function of arterial. After that, the blood pressure continues to drop, as you can see. By the time you get to the vena cava, it's almost zero. The rest of this note is about different type of vessels that you have in the body and the name of the vessels. I'm not going to go through this one because it's all lab material. However, I left it here. If you like to read it as you go through the lab, you're welcome to do so. Therefore, our discussion for a lecture stops here, and I hope you enjoyed it. I'll see you in the next recording.